Welcome to The Alchemist, your ultimate Cambridge physics exam strategy session. Today, we are transforming your basic physics knowledge into gold standard A-star evaluation. I want you to picture a real Cambridge physics past paper question, specifically from the 9702 or 0625 syllabus, staring right back at you. The clock is ticking. The command word is glaring. Let me introduce you to two students who are taking this exam right now. First, we have Alex. Alex is brilliant, memorizes the textbook, but overloads every answer with raw physics facts and completely lacks analysis. Then we have Sam. Sam rushes, panic writes, and completely misses the command word requirements. Today, we are going to look at their flawed answers, complete with the examiner's red pen marks, and show you exactly how to fix them. Our battleground for this transformation, the mechanics of balance, forces, and unlocking rotational equilibrium. We are going to unpack exactly how forces interact to create motion and perfect stillness, and more importantly, how to extract every single mark from the examiner when they test you on it.
Section 1. The turning effect. This is where the exam traps begin. Look at this brilliantly illustrative action on screen using a spanner on a bicycle wheel. A classic exam question will show you this exact setup and ask, describe why pushing the handle causes a twist. Alex, our over-explainer, writes a massive paragraph about the history of levers and molecular structures. 0 marks. Sam, rushing as usual, just writes, because of the push. Maybe 1 mark if the examiner is feeling generous. But how does a straight, linear push magically become a circular twist? And how do we write that to get full marks? You are applying a linear force at a distance from a pivot, yet the result is entirely rotational. To conquer this paper, we need to look closer at the specific terminology the Cambridge mark scheme absolutely demands you use.
Section 2. Couples and torque. This is where we reveal our master strategy.
Let's break down this turning effect by looking closely at how forces are applied, like when turning the handle of a screwdriver. What's really interesting here is that if you only apply one force, the tool just slips sideways. A true twist requires 2 opposing forces. Now, to write an A-star answer comparing these 2 scenarios, you must use our Peel framework: point, evidence, explanation, and link. Your point, a single force causes lateral translation. Your evidence, the screwdriver slips sideways. Your explanation, a true rotation requires 2 equal and opposite forces acting at a distance. Your link, therefore, to drive the screw, a twisting motion is generated by applying these 2 forces. If you structure your physics answers with Peel, the examiner essentially has no choice but to give you maximum marks.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at this definition. In physics, this specific pairing of forces has a distinct name: a couple. If you get a define a couple question, this slide is your Bible. You need 3 distinct elements for full marks. 1. 2 forces equal in magnitude. 2. Opposite in direction. 3. Their lines of action do not coincide. If you just say 2 opposing forces, Sam, you lose the marks. You must specify that their lines of action do not overlap, because if they push directly into each other on the exact same line, they would cancel out. Because they are offset, they create the spin.
And the actual turning effect that this couple produces is called torque, measured in Newton meters. Now pay close attention to the Cambridge syllabus requirement here. When defining torque for a couple, the calculation is the product of just one of the forces multiplied by the perpendicular distance between them. A very common mistake, one that Alex makes constantly, is adding the 2 forces together and then multiplying by the distance. Do not do that. The definition is precise: 1 force multiplied by the perpendicular distance separating the 2 parallel forces. Stick to the Peel structure if asked to explain this, and always emphasize the word perpendicular.
Cambridge loves to test your knowledge with real-world application questions. They might show you a torque wrench and use the command word suggest. Suggest why a torque wrench is necessary in engineering. This isn't just theory. Engineers rely on specific torque measurements to ensure bridges and engines stay securely bolted together. If you over-tighten a bolt on a car engine, it could snap under the massive stress. If you under-tighten it, engine vibrations could shake it loose. You would explain that the built-in scale applies the exact turning effect needed safely. By directly addressing the real-world consequence, you secure the application marks that separate the A students from the rest.
Let's step through the logic of the math together, because calculation assessment objectives require a very specific layout. Step 1, identify the 2 opposing forces, let's say 30 newtons each. Step 2, identify the distance separating them, 25 centimeters. Immediately, your exam radar should be going off. Convert that to standard units, so 0.25 meters. Step 3, multiply the force by the distance. 30 times 0.25 equals 7.5 Newton meters. Always write the formula, show the substitution, state the final answer, and include the correct unit. If you mess up the math but show the formula and substitution clearly, you will still pick up method marks. That is how you play the exam game to win.
Section 3, the principle of moments. Now that we know how to start a rotation, how do we stop it and achieve perfect balance?
Let's watch the transformation happen live. An object is in a state of rotational equilibrium when the twisting forces cancel each other out entirely. Alex wrote a whole page on this, missing the core point. Sam wrote, it stops moving. Let's cross those out with our red pen and apply the green checkmark standard. The perfect, mark scheme-approved answer is when an object has no tendency to change its speed of rotation. This usually means the object is perfectly still, but it's crucial to understand the exact phrasing. This is part of our physics success blueprint. Stop guessing what the examiner wants and start giving them the exact phrases they are trained to look for.
Think of the principle of moments as a structural tug of war, where the clockwise twists perfectly tie with the anti-clockwise twists. Now, read the quote on the screen very carefully. The sum of the clockwise moments about any point must equal the sum of the anti-clockwise moments about that same point. See the phrase about that same point? If you forget to write that in your exam, you lose a mark. It is absolutely vital. You cannot calculate the clockwise moment from one pivot and the anti-clockwise moment from a different spot. They must be referenced from the exact same point to be in equilibrium. Remember that nuance. Let's apply this to a pivoted rod. I want you to imagine a 60-second timer on your screen right now. Let's do this methodically, unlike Sam. Step 1. Calculate the total clockwise moments. We have a 1.2 Newton force at 0.25 meters, plus an unknown force F at 0.35 meters. Step 2. Calculate the anti-clockwise moment, which is 2.5 newtons at 0.40 meters. Step 3. Equate the two sides to solve for F. By setting the total clockwise turn perfectly equal to the total anti-clockwise turn, we can easily find the exact missing force, which algebraically works out to 2.0 newtons. Writing this out step by step is how you guarantee every single available mark. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @aceexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's move into Section 4, Complete Equilibrium Explained. Rotational balance is crucial, but it's actually only half the story. Welcome to the interactive workshop phase of our session. Let's kick off Challenge 1, the data scan. You have 60 seconds mentally to extract the core trend from this comparison. On the left, rotational equilibrium, no spinning. On the right, complete equilibrium, no spinning, and no linear acceleration. The crucial takeaway you need to extract for the examiner is that an object could stop spinning but still be falling downwards or sliding sideways due to an unbalanced resultant force. Complete equilibrium demands zero movement, or rather, zero acceleration, in any direction whatsoever. If an exam question asks for the conditions of complete equilibrium, mentioning only moments will cap your grade. Now for Challenge 2, Find the Flaw. I'm going to read you a sample physics paragraph, and I want you to find the sentence that is losing marks. Here it is. When analyzing multiple forces on an object, we can draw them tail to end. If they form a closed vector polygon, it proves there is no resultant force. Therefore, the object is absolutely stationary and not moving at all. Did you spot the flaw? It's the final sentence. A closed vector triangle means there is zero resultant force, which means zero acceleration. But zero acceleration can also mean the object is moving at a constant, steady velocity. Never automatically assume equilibrium means stationary. That is a classic examiner trap. Let's move to Challenge 3, Speed Writing. You have 30 seconds to write a perfect Peel paragraph explaining how to find a missing force using vectors. Ready? Here's your ideal structure. Point: a closed vector triangle can determine an unknown balancing force for an object in equilibrium. Evidence: by mapping the known 50 Newton downward weight and the 29 Newton pull at 60 degrees end to end. Explanation: because the object is in equilibrium, the resultant force is zero, meaning the vector diagram must return to its starting origin. Link: therefore, by simply drawing the final closing line connecting the end of the second vector back to the start, we graphically decode the exact magnitude and direction of the missing balancing force. Boom, maximum marks. Let's bring all these building blocks together into our ultimate cheat sheet. Feel free to screenshot this slide. The complete physics answering system relies on 3 rules that guarantee top marks. First, command word decoding. Know exactly what describe, explain, and suggest mean. Second, Peel framework application. Structure your paragraphs tightly. Third, the time management matrix. Spend roughly 1 minute per mark available. For absolute complete equilibrium, you must state both bullet points on screen. The sum of the forces in any direction must be 0, and the sum of the moments of the forces about any point must be 0.
I'll leave you with this final, fascinating thought to ponder. Does balance always mean standing still? As we discovered in our workshop, an object gliding through space at a constant speed in a straight line with forces summing to 0 is indeed in perfect complete equilibrium. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.